Okay, hi everyone. Welcome to the live session of week 2. So, again, we'll be doing some questions today. I'll wait for 10-15 minutes for people to join. Okay, then we'll shall start with the questions. Okay, everyone, I think we should start now. Okay, so some topics that were covered in week 2, I hope all of you have uh, seen the videos of the professor. Some topics were algebraic and transcendental functions, even and odd functions, some inequalities related to the some inequalities related to the trigonometric function, inverse of a function, limit of a function of functions, then again algebra of limits, and so on. So I would like to start with uh, a question which was I would like to start with the question we were doing in the previous class, the composition of functions. So I would like to do a question on that firstly, and then move to the topics covered in week 2. Okay. So question number 1. Let fx equals to x minus 1, gx is mod x, s equals to domain of GOF, and s dash equals domain of FOG. Then you have to choose the correct option. Is s is equal to s dash, s is properly contained in s dash, or s dash is contained in s properly. Oh, sorry. Yeah, s dash is properly contained in s. D, s is not contained in s, and s dash is not contained in s. Now, see, g, what will be the function g of fx? G of fx is x minus 1 under root x minus 1. Okay, and g is the modulus of the function, so this will be under root x minus 1. Now this under root always opens in positive, so this is nothing but under root x minus 1. So the domain is when the domain is all those x belonging to R such that x minus 1 is greater than or equal to 0. That is, what is this interval? 1 to infinity. So s is 1 to infinity. Now f of gx is f of, what is the function g? Mod x. And what does f do? Under root of x minus 1. So this will be mod x minus 1. So domain is all those x belong to R such that mod x minus 1 is greater than or equal to 0. That is the interval x, all those x is that mod x is greater than or equal to 1. That is the interval minus infinity to minus 1. 1 is included because here we can have 0 also. So 1 is included, union 1 to infinity. Right? So our s dash is minus infinity to minus 1, union 1 to infinity. So this is s dash, this is s. So our option s is properly contained in s dash. So our option B is correct. Okay. So this is a warm up for the from the last uh last topic from the last week. Okay. So let us now do some questions related to the week 2 topics. So I would like to do first question on inverse of a function. Question number 2. Sorry. Question number 2 is, which of the following gives an inverse of the function y equals to x square minus 1? So A option is y equals to under root x plus 1, y with y greater than equal to 1, y equals to under root x minus 1 with y less than equal to 0, y equals to minus x plus 1 with y less than equals to 0, and D option is y equals to minus. Now see what is the function. So our function y equals is given to be x square minus 1. So what is the domain of the function? It is defined for all x in R. And range is x square is always positive, implies x square minus 1 is always greater than equal to minus 1. So range is not so. I mean, you know that for you have just seen that fx will always be greater than equal to minus 1. So this set is contained in the the range is contained in this set, in fact, because and for every y belonging to minus sorry to minus 1 to infinity, minus 1 to infinity, if you take x to be under root of y plus 1, then f of under root of y plus 1 is under root of y plus 1 square minus 1, which is y plus 1 minus 1, which is y. So every y belonging to this set has a pre-image, which is this, and also this under root y plus 1 is defined because we have y in y is greater than equal to minus 1, so y plus 1 is greater than equal to 0. So our range has to be nothing but this set. So now see that this function, the function has an inverse when the function is 1 when on 2. But on R, you see that f of a and f of minus a have same values. But a is not equal to minus a, so the function is not 1, 1 on the whole domain. But if we restrict the domain to R plus and R minus, then the function is 1, 1. And on to with the range this. Right? Because range will be the same because the f of a and f of minus a will still give the same value, which will lie here. Okay. Now we can have the inverse on R positive and R negative. Now see how to find the inverse. Fx is given to be x square minus 1. We have to find f inverse x, that is given y belonging to minus 1 to infinity from the range. We have to find x. So what do? Y such that y equals to fx. So y equals to fx meaning y equals x square minus 1. So y plus 1 equals x square. X equals to plus minus y plus 1, and again this makes sense because y belongs to this set. So x is nothing but f inverse y. So our f inverse y is plus minus y plus 1. Or if we write it in terms of x, f inverse x is plus minus x plus 1 for x greater than equal to minus 1, right? So our inverse function is, if we denote this by y, this is y equals to plus minus x plus 1 for x greater than equal to minus 1, right? But also you have to note that for uh, that y is equal to x plus 1 has the domain minus 1 to infinity and y positive, and y equals to minus x plus 1 has the domain. These two are the inverse functions, and these two are the inverse function, meaning when we restrict the domain to a real, positive real, and negative real. So if we restrict the domain to positive reals, then this will be the our what do you say, the inverse, and this will be the inverse for the negative real. Has the domain minus 1 to infinity and y less than equal to 0, right? That is x belongs here, x belongs here. So our correct option is y equals under root x plus 1 with y. A is wrong, y equals minus, again this is wrong, b is wrong, and y equals to minus x plus 1 with y greater than 0. So C is the correct option. Again, D is the wrong option. So our correct option is C. Okay, I hope it's clear for everyone. If not, you can always ask in the ask a question session section in your dashboard. All right, let's move to the next question. This is question number 3. The next question is on even and oddness. Given fx equals to sin x, tan x, gx equals to x plus secant x, and hx equals to x cube under root x cube plus 1. Determine the evenness or oddness of the given functions. Okay, so it's not difficult. You just have to see f of minus x, g of minus x, and then h of minus x, whether they're equal or they're negative of f of x, or if they're not, then it will be neither even neither odd. So this is sine of minus x, tan of minus x, which is minus of sine x, and this is minus of tan x. So this is sine x tan x, so which is equal to fx, implies f is even, right? Now g of minus x is, what is g? Minus x plus secant minus x, which is minus x plus secant of x. Secant absorbs the negative, so this is not equal to minus gx and not equal to gx also, right? Implies g is neither even nor odd. Last function is hx equals under root x cube plus 1. So h of minus x is under root minus x cube plus 1, which is minus of x cube plus 1, which is not equal to, again, h of x or h of, h of x or minus of h. Implies h is neither even nor odd. So there are functions which are neither even nor odd. right? So the motive of this question was to tell you that there are functions which are neither even nor odd. All right. Next question. The domain and range of the function fx equals 3 cos 2x plus pi by 2 plus 1 are, you have options: A, s equals to minus infinity. The domain is denoted by s, range by r, minus s to infinity, r equals minus 2 to 4, b, s equals minus infinity to infinity, r equals minus 2 to 4. C option is s is minus 2 to 4, r is minus infinity to infinity. D option is s is minus 2 comma minus 4 and r is minus infinity to infinity. Now the given function is fx equal 3 cos 2x plus pi by 2 plus 1. Now all the trigonometric functions are defined for the whole of the R. So this function will have no problem at any point. So the domain is minus infinity to infinity. So options C and D are incorrect. Now we have to find whether the range includes these 2 points minus 2 and 4. So the range, firstly see that cos 2x plus pi by 2 will always take values between 1 and minus 1, right? And 3 cos, if you multiply it with 3, minus 3 cos 2x plus pi by 2 will take values between minus 3 and 3. And if we add 1, 3 cos 2x plus pi by 2 plus 1, this is nothing but fx minus 2 less than fx less than 4. So this inequality will not create any problem at any step. So we have range equals minus 2 to 4, because cos of this can take value minus 1 and 1. So whatever, at whatever point this cos function to cos of 2x plus pi by 2 will take the value 1 and minus 1, 1 or minus 1, there the given function will take the value minus 2 and 4. So you can easily evaluate that. So the correct option is A. So A is the correct option. Okay. Question number 4. Now we are moving to the finding the limits of the function. Limit extends to 0, pi minus 2 of fx by x is 1 by 2. You have to find then limit of x tending to 0, fx is what? Our options are A, 0, B, pi, C, pi by 2 and D, infinity. So in this week sir has not covered this limit, infinite limits. In the next week class, if you have seen the week 3 uh, tutorials already, then sir has covered it there. Anyway, so if you have seen week 2 videos, sir had discussed that if the limit in a rational type of function, if the limit of the denominator at the given point where we have to find the limit goes to infinity is not a finite term, but the limit of the ratio is finite, then the numerator has to go to 0. It makes sense, no? Because if the limit of the numerator goes to some finite quantity, and if the limit of the denominator goes to infinity, then the overall limit has to go to infinity. Or if the limit of the numerator goes to infinity, again the overall limit will have to go to infinity. But we have here that limit of the ratio is well defined, it exists. So the limit has, and the limit of the denominator, or meaning that limit x tending to 0, 1 by x is infinity, then then what do we say? That the limit of the numerator has to go to 0. So what conclusion do we have? That infinity, or we can say the limit of the denominator at 0 goes to 0, and limit of the ratio pi minus 2 fx by x is 1 by 2 finite, implies that limit of x tending to 0, that is the numerator, 2 minus fx, or this is same as saying that limit of x into 0, 1 by x is infinity. This has also been covered in week 3. So this is 0. And now by algebra of limits, we can distribute the limits. So limit x tending to 0 pi minus limit x tending to 0 2 of fx is 0. Again, using the algebra of limits, since firstly this is constant, so its limit will be the same. This is a constant function pi, this is pi, and minus 2, this is a scalar, this can come out again by algebra of limits, is this is nothing but f of x equals 0, implies pi equals 2 limit x tending to 0 f of x. This will imply that limit x tending to 0 f of x is pi by 2. So you have been given limit of the ratio to be finite, and the limit of the denominator is going to 0 at the given point where you have to find the limit. So we can conclude the limit of the numerator at that point has to be 0, and from that we have evaluated limit of the function fx which was present in the numerator. So the correct option is, of course, C. Okay. So this is how some results are. This is the application of basically the results that are discussed in class. Question number, this would be, I think, question number 4. No, I have, yeah, this was question number 4. This was question number 5. Now question number 6. Just give me a minute, I'm sorry. Okay, so we were on the next, we're moving to the next question. Next question is again on limits, algebra of limits. So most of the questions today we shall discuss will be on algebra of limits only, because that was the major topic covered last week. And your assignment, week 2 assignment questions are also, I think, basically mostly based on that. So question number 6 is limit x tending to 2 x square, limit x tending to 1 gx is 2, then limit x tending to 2 g of x minus 1 is what? A is 0. Options are A 0, B 1 by 2, C 1 and D infinity. Now you have been given a relation between x square and the limit of the function at the point 1, and you have to find the value at the limit at point 2 but of the function g of x minus 1. So let's see what information can we extract from the given relation. First, about the limit gx, let's try to do this. Let's try to see open what is happening here. So this is limit of x tending to 2 x square, limit x tending to 1 gx is 2. Now see, this limit is a scalar, that when limit is applied to a function it becomes a scalar, so it can be taken out by, again, by the algebra of limits. So this is nothing but limit x tending to 1 gx into limit x tending to 2 x square equals 2. This was the trick here. You don't have to get confused by seeing two limits here. So this is a polynomial type of function. We can simply put the limit here. So this becomes, this is 2 square equals 2. So we have got limit of is 2 by 4 equals 1 by 2. So the information we have is about gx is of about the limit at the point 1 is 1 by 2. What do we have to find? To find limit of x tending to 2 g of x minus 1. Now see, just assume we know the limit at the point 1. We assume this argument inside the function to be, let t equals x minus 1. Okay, we have to find the limit at the point. We have the information of the limit at the point 1. We have to find the limit at the point 2 but of the function g of x minus 1. So we have put t to be x minus 1. Now we know that if t tends to 1, we know the limit. Okay, so when t tends to 1, x is tending to t plus 1, that is 2. So what do we say that? So what information we have about, we already know the information about g at the limit of g at the point 1. So we say that limit t tending to 1 gt equals to 1 by 2. So this implies t was x minus 1, t is x minus 1 tends to 1, g of x minus 1 is 1 by 2. It implies limit x tending to 2, x minus 1 goes to 1, then x has to tend to g of x minus 1 is 1 by 2. So this was, or this is exactly what we had to find. So our correct option is 1 by 2. Alright, I hope it was clear for everyone. Okay. Alright. Question number, this would be question number 7th. Again, algebra of limits, limit x tending to 0 to fx plus 3gx equals 3. Limit, these are the relations that have been given. X tending to 0, fx gx equals to 1 by 3. Limit x tending to 0, fx is greater than 1 by 2. Then limit extending to 0 fx plus gx is what? Your options are minus 4 by 3, minus 2 by 3, 2 by 3, and d 4 by 3. Now you have some relation between the limit of fx and limit of gx. You have to this gives the idea that you can kind of make a system of equations from here and then try to find the limit of fx and gx at the point 0 and then put it here to get the required answer. So what do we see? So what do we assume that let limit of x tending to 0 fx is a, limit of x tending to 0 gx is b. Okay, now from the given relations we have limit x tending to 0 fx 2fx plus 3gx equals 3 implies limit x tending to 0 2fx algebra of limits we can apply simply you can do that 2 limit x tending to 0 fx plus 3 limit x tending to 0 gx is 3. So 2 we have assumed limit x tending to 0 fx to be 1, limit x tending to 0 gx to be b, then this is 3. So this is one of the equations. Now second relation we have been given is limit x tending to 0 fx gx is 1 by 3. So since we have assumed that limit of x tending to 0 fx and gx both exist, then we can separate the limits, but take care that this cannot you cannot always do that. Okay, like for example limit of x tending to 0 sine x by x is 1, but see limit of 1 by this is 1 by x sine x, this is infinity and this is 0. So individually they are going to, so you cannot simply uh, separate it because not both the limits exist, but still the limit of the product exists. So be careful with this step. Okay, so limit x tending to 0 we can separate it because both limits, just don't blindly do anything and everything. Okay, just because we have assumed both limits exist finitely. So this is a into b is 1 by 2. So this is one more equation you have got. So you have two variables, two equations, you can solve it. So from here, so this is given to be 1 by 3. So here from here b implies b equals 1 by 3a. Just put it here. The equation is 2a plus 3b equals 3. So if I put it 2a plus 3 into 1 by 3a equals 3. So we have 2a square plus 1 equals 3a. So 2a square plus 3a plus minus 3a plus 1 equals 0. So we have 2a square minus 2a minus a, right, plus 1 equals 0. 2a common, a minus 1 minus a minus 1 equals 0. So you have a minus 1, 2a minus 1 equals 0. So you have a equals to 1 or 1 by 2. But you have, but what is a? A is the limit of fx at 0. But given that limit extending to 0 fx is greater than 1 by 2, strictly greater than 1 by 2, implies a cannot be a has only two options. Either it can be 1 by 2 or it can be 1. But you have been given that limit at the point x tending to 0 fx, limit at the point 0 of fx is strictly greater than 1 by 2, so it cannot be 1 by 2, so A has to be 1, implies B was 1 by 3A. So B equals to 1 by 3A equals 1 by 3. And so A equals to 1, B equals to 1 by 3, that is limit x tending to 0, fx is 1, limit x tending to 0, gx is 1 by 3. But you did not, your original question was not to find this. So limit x tending to 0, fx plus gx will be, by algebra of limits, limit x tending to 0, fx plus limit x tending to 0, gx is, so limit x tending to 0, fx is 1, this is 1 by 3, so this is 4 by 3. Okay, so our correct option is D. All right. Okay, I hope every question discussed till now is clear to everybody. We'll do a few more questions. So till now we have done some questions on limits where the limit existed, right? It existed and existed finitely, but there are scenarios when the limit does not exist, or limit is either infinity, if those are called infinite limits, or and till now we were seeing limits at a finite point, that is limit extending to 0 or 1 or 2 or so on and so forth. But there is something called limits at infinity. Again, all of these topics have been discussed in the next week classes. So you can look there and we'll do the questions related to that in the next week. But I would just like to give a glimpse of the scenario where the limit does not exist with a simple graphical example. And this is our next question. So this would be question number 8, right? For the function graphed down here, find the following limits. Either find the following limits if they exist, or explain whether they do not. So, okay, firstly I shall draw the graph. I'm sorry about bad drawing skills, but I'll try. Okay, so x-axis, y-axis. This is the line y equals to 1. This is 1, this is 2, this is 3. So the graph is like just assume this to be 1. Okay, then we have between 2 and 3 graph to be something like this. Okay, and then we have something like this. Okay, Just see. Okay. And like this, and here we have a hollow circle, and here we have a hollow. So these, I hope you know that these hollow circles mean that the point is not included in the graph, and this filled circle means that that point is included. So, okay, I think I have made a. What is the graph from 1 to 2? I did not make that. So graph will be right. Okay, and this point will be 2. Okay, yes. So this point is included, this point is included, and this point is included. Now, and these 2 points are not. These are hollow circles. That is, at the point x equals to 1, the value is not 1, but it is 0. At the point x equals to 2, the value is 1. At the point x equals to 3, the value is not 0, but it is 1. Okay, you have to find limit x tending to 1 gx, b limit x tending to 2 gx. So this is the function gx, and this is x, and c limit x tending to 3 g. So keep some things in mind, that whenever we have to evaluate the limit of a function at some point, we do not care about the value of the function at that point. We care about how the function is behaving near that point. So we see that now when we are in R, we have two ways of approaching one point. Either we can do it from left or we can do it from right. I from left and or from right. It's like we can reach one either from the points less than 1 or from the points greater than 1 in the neighborhood of 1. That is why we discuss or see the limit in this 1 plus delta, 1 minus delta, 1 plus delta. We try to find this delta for a given epsilon, right? Now, from both the sides, when x is approaching to 1, the limit should approach a unique point. If it does not, then we say that the limit does not exist. Okay, if it is approaching to different points from different sides, then we say that the limit does not exist. Now see from the graph, okay, so the first is limit x tending to 1 gx. So you can see from when, so solution of a limit x tending to 1 gx does not exist. Why is that? When we approach, because when x approaches 1 from the left, from the left, from here, then gx is taking the value 1, right? At all the points when x is here, 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 it is going to 1. But when I'm again saying, you do not care about what the value x is taking at the point 1. You do not. But around the point 1, the x is less than 1, it should take the value 1, right? And from the right, when x approaches, it takes the value 0. It takes the value, that is limit takes the value, or gx, or we can say from the left, gx approaches gx will, when x is going from left from all these points, gx will can only approach 0, or sorry 1. But when x is, it cannot approach 0, right, at any cost. But when x is going to 1, when x is decreasing to 1 from the right, it will be taking all these values and will be approaching 0. So when x from the left gx approaches 1, and when x approaches 1 from the right, gx approaches 0. Implies there is no single number, there is no one unique number L that all the values get arbitrary, that all the values get arbitrarily close to as x tending to 1. So there is no single number where gx approaches when x is going to 1. There are two different numbers, so we said that the limit does not exist. But for the point x tending to 2, either from the left, we see it will go here, or it will take the value 1, or from the right, if we approach 2, sorry, it will be like increases to 2, x increases to 2 from the right, it will approach 1. So the limit, limit x tending to 2, sorry, x tending to 2, yes, gx is 2, it exists and the value is 2. Now at x tending to 3, now x tending to 3 from the, if from the left, where will it go? From the left it will approach 0, and again from the right, if we increase to 3, then it will approach 0. We do not care that g3 the value is not 0, it is 1, but the limit is 0. Such a function is called discontinuous function. There is a jump at 0. The function is not continuous. So the limit exists again at the point 3, and gx is 0. So this is 1, not 2. Gx is approaching this point 1, here 0, and here the limit does not exist. So this was kind of an example where there's exist a point in the function, in the domain of the function, where the limit does not exist. There exists a good point where the limit exists, and there exists a point where the value of the function is not the same as to where it approaches at that of when x approaches that point, but the limit exists. There's another concept which comes into picture, is called continuity, that the function at the point 3 is not continuous. It is not it's not a point like 2 where the function is also approaching 1 and the function value of the function at 2 is also 1, but the limit exists at 3. That is certain, right? So this was a good example to understand kind of concepts of a limit through a graph. Okay. Some next question. So this should be question number 9, right? Question is just a simple question on geometry. A point P in the first quadrant on the parabola y equals to x square. Point P in the first quadrant lies on the parabola y equals to x square. Express the coordinates of P as functions of the angle of inclination of the line joining P to the origin. Okay, since this is a question on trigonometry, I'll wait for 5 minutes for you guys to try and I'll be back in 2-3 minutes. Okay, I hope you have tried the question. So the question is, given a point P in the first quadrant of the parabola, so the parabola looks like y equals to x square, looks like this. Right? Now any point on the parabola will be x comma x square, and this is the point P in the first quadrant. Now the question is the angle of, you have to express this coordinate in the terms of angle of inclination of the point of the line joining P to the origin. So this is origin, this is the line joining P, so this is the angle of inclination. In terms of x and x square, this length will be y x square and this will be x. So you see the tan theta is perpendicular upon base, this is 90 degree, so this will be x square upon x, so this is x. So this don't get confused, this x just fix, think it like fix the point x comma x square on the parabola in the first quadrant, and you have to express this point in terms of angle of inclination of the point of the line joining P to the origin. So this is x, so tan theta is x. So the points coordinates are x comma x square, in terms of angle is tan theta comma tan theta, tan square theta. Right? Okay. So this was not difficult to see. It was just a geometric exercise related to trigonometric questions. I hope these two have been covered in your 11th and 12th standard as well. Right? So moving to next question, which is based on even and oddness. Question is question number 10th. If fx is odd, can anything be said? Can anything be said about the function about gx equals fx minus 2? What if f is even instead? Can anything be said about the same function? Give reasons. Now see, if fx is odd, if fx is odd, implies f of x equals to, sorry, f of minus x equals minus of fx for all x in the domain of f. Now g of minus x is f of minus x minus 2. This is minus of fx minus of 2. And minus of gx is minus fx plus 2. So if we consider if g is odd, implies g of minus x equals minus of gx, implies minus fx minus 2 equals minus fx plus 2. So this get cancelled, so implies minus 4 equals 0, which cannot happen. Implies, at least what we are certain about g is that g cannot be odd. Now can g be even? So if g is even, implies g of minus x equals g of x. So g of minus x is minus fx minus 2, g of x is fx minus 2. So this is implies fx equals to 0. So g is not even unless fx equals to 0 for all x. So if the function fx is identically 0, then only G can be even. Otherwise, G is also not even. So what can we say, that G cannot be even unless fx is 0, and G cannot be odd in any situation. So these are two implications we can get if f is odd. Now next question is, now what if f is even? Then f of minus x equals f of x. Then g of minus x is f of minus x minus 2. This is f of x minus 2. This is gx. Then if f is even, then we are certain that then gx is also even. Okay, so these are the two implications we can get if f is odd and if f is even. So if f is even, if we subtract some constant from it, the function will remain even, and if f is odd, if we subtract a constant, the function can never be odd, and it can be even if and only if the function f is identically 0. All right. One more question on even and oddness. Question number 11. So question is if gx is an odd function defined for all values of x, can anything be said about g of 0? So 0 is a special point because minus 0 is equal to 0. That is why the question is asking about g0. So if g is odd and we know that g0 exists, matlab g0 is defined like 0 is in the domain of the function, then g of 0 equals minus, or simply g of minus 0 equals minus g of 0. G of minus 0 is nothing but g of 0 equals minus g of 0, implies 2 times g of 0 is 0, implies g of 0 is a 0. So if any function is odd and if we know that the function takes 0 in the domain, the function takes the function at the point 0 is defined, then it has to take value 0. Okay, it cannot take any other value. If it does, then the function will have a contradiction with the oddness. So these were some questions, exercises on the related to the evenness and oddness of a function. Now next question is on evaluating the limits. Limit extending to 4, evaluate the following limit. Limit x tending to 4, 4 minus x upon 5 minus x square plus 9. So in functions like this, see that when x tends to 4, it is forming a 0 by 0 form. So we try to avoid such forms and do some manipulation to avoid this 0 getting in the denominator. So whenever we have an under root or this ratio type of functions, we try to rationalize it. So please try this question. It should not be difficult. Please try and wait for 2-3 minutes again. Okay, let's start with the calculation. I hope you are able to do it. So if when we rationalize, so I'll just see this function and then apply the limit, just for not writing limit x tend to 4 this notation every time. Five plus x square plus 9 upon 5 plus x square plus 9. You multiply this. In fact, no need to even multiply because you have to put the limit at the end. So denominator is this a square minus b square, 25 minus x square plus 9. So this is 4 minus x, 5 plus x square plus 9. So usually this x minus 4 factor will cancel out. That is why we then only will be able to avoid this x tending to 4 becomes 0 in the denominator. So this will be 16 minus x square. So this is 4 minus x, 5 plus x square plus 9 upon 4 minus x, 4 plus x. So this cancels. So if we put now x tending 4, this denominator is not becoming 0. So limit x tending to 4, 4 minus x upon 5 minus x square plus 9 is limit x tending to 4. This function equals to 5 plus under root x square plus 9 upon 4 plus x. So this is, you just have to put the value because everything is defined now. 16 plus 9 upon 4 plus 4. This is 5 plus 25 under root 10 upon 8 to 4 to 5. So the value of the limit is limit x tending to 4, 4 minus x upon 5 minus x square plus 9 is 5 by 4. Okay. So next question is based on sandwich theorem, which sir has discussed in class. So go through it and then come back to this question if you don't know. Sandwich theorem, as the name suggests, is if a function is sandwiched between two functions, then the limit of if in the limit of both the functions on either side of our given function is equal, then the limit of the function between them has also would be the same as the limit of the functions on its side. Sandwich theorem, or in fact you can call it the squeeze theorem. That is, just to recall, and if f, g, h are real valued functions such that fx less than gx less than hx for all x belong to domain of the definition of each of the functions, and for some a belonging to R, if limit x tending to a fx equals to L equals limit x tending to a hx, then implies that limit x tending to a gx is gx exists and is L. Okay. So now the question based on that, evaluate the limit hx equals x square cos 1 by x cube. Now you cannot simply just integrate, you have to evaluate the limit at, simply just integrate it. Simply just divide the limit on these two functions, because you don't know whether the limit of this exists or not. So whenever there are trigonometric functions, it is really helpful to use the sandwich theorem, because you know that this function will at least exist or will take the values between 1 and minus 1. So we know a function between which this function is sandwiched at least for all x belong to R, x not equal to 0. And then when we have to find the limit, we don't usually care about the value of the function at the point 0. Right? So now we multiply x square is a positive function, so if you multiply with it, no change of sign will happen in the inequality. So our function is sandwiched between these two functions, minus x square and x square, for x not equal to 0, and we don't even care about the value of the function where we have to find the limit. So x square less than hx less than x square implies limit x tending to 0 okay. Now these are fx and gx if you call it. Then limit of x tending to 0 minus x square is 0 is equal to limit x tending to 0 x square, implies by sandwich theorem, implies limit x tending to 0 hx is 0. So see, this is very helpful. Sandwich theorem is very helpful in finding the limits, right? Okay, so this we have, I think, done enough questions about the limit of the functions, which was the main idea, which was the main topic to be covered in this week. In fact, the limits of the function at finite points, at a finite value, you can say. So one question is just to warm up exercise. Question 13, this is question 14. F from R to x belonging to R minus 1 x less than 1 is defined from fx equals x by 1 by x. I should not write it like this. I should write find the domain. Again, a domain and range functions, because it is very helpful. So it's not a domain. It's a one question on 1 and on 2. So I'm writing it correctly. I'm sorry. F from R to the range of the function is R minus 1. Fx is x upon 1 plus x. X belong to R. Show that the function is 1 1 on 2. 1 1 means that for any point x and y, or you can say that every point in the domain goes to a unique uh, image in the range, or the right, or uh, and onto means for any point if you pick in the range, it has a in this set codomain, it has a pre-image, then that codomain is the range. So to show that 1 1 and on 2, 1 1 we show that if 2 points are going to the same value, then those points, meaning that if 2 points are going to the same value, then that point, that this case cannot happen, right? That every point is going to a unique point in the codomain. So to show, first of all, Or another way of saying ma12 is that different points will map to different images, right? The if fx equals to, so okay, so first is fx, you can define as fx x upon 1 plus x, when x is positive, x upon 1 minus x is negative, because mod x we know can be minus x or x. So 1 1. Case 1 is, so we have to show for any xy belong to the domain of f such that fx equals fy implies x equals to y. So we take four cases that if x positive, y positive, and fx equals to fy implies x upon 1 plus x is y upon 1 plus y. Just put the value of fx and fy, cross multiplying x plus xy is y plus xy equals implies x equals y. So in this case, the function is taking a, so different value, different points in the domain are taking different values. Case 2, when x is less than equal to 0 and y is greater than equal to 0 and fx equals to fy. So first of all, x cannot be equal to y, right? Because x is positive, y is negative. But in fact, fx is not equal, it will not be equal to fy, because x, if it is, y is negative, y minus y, x minus xy equals y plus xy implies x minus y equals 2xy, right? So this is okay. So just take x to be positive and y to be negative, because I have taken that value. So this is positive, this is negative, this whole will be positive. But this is positive, this is negative, this will be negative. Cannot happen. So contradiction implies fx not equal to fy. So this case so cannot occur. So this case cannot occur. That fx and fy will already take different values because x is not equal to y here. Then case 3, x again a case the 3 can be x less than 0, y greater than 0. Similarly can be handled as x less than 0, y greater than 0, same as case 2. Case 4, x less than 0, y less than 0, fx equals to fy will imply x upon 1 plus, sorry, x upon 1 minus x equals y upon 1 minus y, cross multiplying x minus xy equals y minus xy implies x equals to y. So thus the function is on 1 1. ठीक है, अब on to for any point y belong to minus 1 to 1, because this was the range here, the interval minus 1 to 1, you have to show that exists x belong to domain such that fx equals to y. So we make two cases if y belongs to minus 1 to 0. So I'm not including 0 just to avoid, because 0, note that 0 belong to minus 1 to 1 imply we have f0 equals 0 implies 0 has a pre-image. Now for y belong to minus 1 comma 0, right? You have to find x such that fx equals to y. We'll make we'll make we'll take the reverse step. So fx equals to y means if x can be, so either this can be either x upon 1 by x equals to y, or x upon 1 minus x equals to y. But this is negative, right? And if x is positive, then x upon 1 plus x is always positive for x greater than 0. So this cannot happen. So when y is negative, so this is the only case that can happen. So x equals to y minus yx, x plus yx equals y, x equals y upon 1 plus y. So this implies f of y upon 1 plus y equals y when we take y from -1 to 0. This is the preimage. Now if y belongs to 0 to 1, that is y is positive, to find again x such that fx equals y. Now fx again can be x greater than equal to 0, x upon 1 minus x equals y. Now if y is positive, this is positive, this is the only case that can happen. X upon y minus x, this will be negative, this will be positive, cannot happen. So x has to be positive, and x, what will be x? X equals to y plus yx, cross multiplying x minus yx equals y. We take x common, x equals y upon 1 minus y, and y was less than 1. So this is positive. So implies f of y upon 1 minus y is y. So we have taken any point in the domain. Y 0, we have shown 0 is the preimage. For y positive, we have shown y upon 1 minus y is the preimage. And for y negative, we have shown y upon 1 minus y is the preimage. Thus, f is onto. Hence, proof. This is what we had to prove. I hope you were able to understand this question. Okay. So that's it from my side for today. I'll wait for people if anybody has doubts to ask me. I'll be here. Thank you. We'll meet next week.